Welcome to Prince Maths Clinic, the e-learning solution at your pace and time. It's a beautiful day, and here we are in continuation of the Diophantine equation. Remember, in the previous class, we looked at this question using the general approach, and I promised you that in today's class, I will be using another method. And the method I will be using today is called the Newton's approach, or the Newton method of solving the Diophantine equation. And I'll be using just 4 steps in solving the Diophantine equation. First step I would carry out in this Newton equation is to first express the equation in the form of f of x. But before I continue, like the video so that YouTube algorithm can share the video. So, having said that, let's look at the solution using the 4 steps I've listed on the board. The first step, like I said, is to put this equation in form of f of x. So, I will move this 8 here. This 8 will become negative. Alright, so let's go. This is what we were given. Therefore, putting it in form of f of x, I can say that f of x will become everything I have here, just to move this here. So this will become 2 to the power of x plus x to the power of 2 minus 8. So I've achieved this first step. The second step now is to find the derivative of f of x. Finding derivative means to differentiate. That's what it means. So, I want to differentiate 2 to the power of x. I will do it separately here. Watch. Now, I want to assume that my y is equals to 2 to the power of x. And I want to differentiate this. So, watch how I'm going to achieve this. To differentiate something like this, all you need to do is to take the natural log of both sides, which is ln. So, I'm going to ln both sides. So if I ln, this become ln y, then this become ln 2 to the power of x, right? Good. So I can now use the rule that says when a log is carrying a power, the power multiplies the log. I can use it here. So this become ln y is equals to x ln of 2. So at this part, I'm going to use the implicit function to deal with this part. So what do I do to achieve this? Because this is differentiating y, right? Remember, you differentiate dy dx, right? With respect to x, but I want to differentiate y with respect to y. So what do I need to do? When I do that with implicit function, you know, normally if you differentiate ln x, you are going to get 1 over x. Is that not so? Good. So, but because this is not x, this is y, I am going to still say 1 over y. But because I'm differentiating y and not x, I'm going to put here as dy dx. Good. Then, at this part, what I'm going to do is that I'm going to treat ln 2 as a constant. You know, if you want to differentiate something like 3x, if you differentiate this, you get 3, right? You just pick out the constant, the variable goes. That's what I'm going to do. So if you differentiate x ln 2, right? Remember I said you have to leave this because it's a constant. So if you differentiate this, this becomes ln 2. So to achieve dy dx, therefore here, dy dx will now become y times ln 2. And what is y? Remember we said that y is 2x. So this becomes 2 to the power of x ln 2. Good. I'm going to provide a video, maybe subsequently, on how to solve questions like this. But in today's class, let's just learn this so that we can make progress on this equation. That we now know that if we differentiate this, so how do I symbolize differential, I can put this as f prime of x. That's the meaning of differentiation. So when we differentiated this, we add what? 2 to the power of x ln of 2. That is the result. So if it is 2 to the power of, if it's 3 to the power of x, it will be 3 to the power of x ln of 3. If it is 5 to the power of x, it will be 5 to the power of x ln of 5. Good. So if we differentiate this using this principle, x to the power of n, so dy dx will just be what? N times this will multiply this, then you take out 1 from the power. So using that method here, x to the power of 2, 2 times this will become 2x, then take 1 away from the power, you have 1. And x to the power of 1 is still what? X. Good. So it means if I differentiate x squared, I'm going to get 2x. Then this is a constant. In differentiating a constant, here is it. Y is equals to 8. It has no x, but I can dash it an x. So if I say x to the power of 0, it becomes 1. Anything to the power of 0 is 1. And 1 times 8 is still 8. So nothing has changed. So using that same method, 0 will multiply this. So 0 multiplied by 8x, 0 minus 1. Then because 0 is multiplying this, everything has rendered to become 0. Good, so there will be nothing here. So it means that my differentiation of f of x gives us this. Good. I have achieved step number 2. The next important step is to select an initial guess value, right? And I've said that let x naught be 1. It is that value we are going to use to iterate. That is that value we are going to use to apply the Newton's method. But what does it mean to iterate? Iterate means to do something repeatedly until you get a small value that is sufficient enough. That's what it means to iterate in mathematics. And let's look at this method. I want to give you the formula now. Good. So, using the Newton method, so to iterate using Newton's method, so here is the Newton method. Here is what I'm going to use to iterate. So we have said that let x naught be equals to 1. So if x naught is equals to 1, it means that my x1 here, therefore, x naught. So that is the interpretation of this formula. My x1 will be x naught minus f. Anywhere I see n, I'll just put naught. So in order to iterate very well, here's what I'm going to do. I am going to use this formula now to now simplify this. So it will look like this. So anywhere I see my f of xn, like I said here, I'm going to put 1. So this is 2 to the power of 1 plus 1 to the power of 2, then minus 8. Then everything here, remember, is over the derivative, which is this. So anywhere I see x again, I'm going to put 1. So this means 2 to the power of 1 ln of 2 plus 2 times 1. Good. So let's see what we are going to get using that. 1 minus 2 to the power of 1 is still 2. 1 squared is still 1 minus 8 over, then 2 to the power of 1 is 2. Then ln of 2. So it then means that this will become 3 minus 8, which is minus 5. So minus and minus, we eventually change it to plus. So this will become 1. So eventually this will become 1 plus 5 will be on top over. So let's treat the denominator. So if I say 2 times 0.6931 plus 2, I'm going to get 3.3862 So 5 over this, what will it give us? We are going to get 1.7, 1.4765. So if you add this, x1 is 2.4765. So you can approximate this to 2. But if you are not okay with the approximation, you can iterate for the second time, picking another value of x. So we picked 1, you can pick the value for 2 here, and let's see how it's going to look like if we pick 2. Is equals to 2. So that means that my x1 will now become 2 squared is 4, plus another 2 squared, that's 4. 4 plus 4 is 8. 8 minus 8 is 0. Good. So everything here renders to 0 over, so whatever you get here, we know that our ln to 0.6 something multiplied by 4. Everything here, no matter what it's going to give us, because there's 0 at the numerator, renders to 0. So 2 minus 0 is equals to 2. So you can see that iterating for the second time gives us the exact value of 2, which is the solution to this particular problem. So I would advise you to pause this video, look at the solution critically so that you can understand how to use the Newton approach to solve Diophantine equations. So, till we meet again, keep practicing and keep succeeding. Bye for now.